Okay, 9.2 Electrochemical Cells. Pleased to say this is a bit shorter than the 9.1 marathon that you maybe just watched. So we're going to look at voltaic and electrolytic cells. So we'll start with voltaic, and what we're using here is a chemical reaction to generate electricity. And what we've got is a metal dipping into a solution of its ions, another metal dipping into a solution of its ions. And we have a voltmeter. That voltmeter is connected to the metals by just a wire. Going between the solutions, we have a salt bridge. Right? That's our salt bridge. And salt bridges would be something like, you can make them in the lab just by taking some filter paper, and if you soak it in something like potassium nitrate or potassium chloride, you end up with a salt bridge. So my electrons are going to move through the metal wire. The salt bridge completes the circuit, and it allows for the passage of ions to move around. So if I think of my zinc and zinc sulfate, I've got my copper sulfate. My zinc is the more reactive of these metals. Right? Zinc has a greater tendency to give up electrons. Right? We've seen it in the past. We've seen this reaction in the last section. CuSO4 goes to Zn SO4 plus Cu. Right? We've seen that spontaneous reaction in the last section. So my zinc is going to have a tendency to do that. Right? It's going to give up its electrons. Now those electrons are going to go over to this electrode, where they're going to be picked up by the copper ions. Right, so these are my two changes that are taking place, my two half equations in my two half cells. And wherever we see, this is an oxidation, wherever we see an oxidation, we refer to that as the anode. Conversely, wherever we see a reduction, we refer to that as the cathode. And that's the way to remember which is called the anode and which is the cathode. Right? Wherever there's oxidation, it's the anode. Wherever there's reduction, it's the cathode. So a way of representing this in a different format would be, there's our zinc solid, and that single line means that there's a phase boundary, but it's in contact with zinc ions, which are in solution. We've then got our salt bridge, which connects it to the copper ions, which are in contact with copper solid. Now we can go beyond this. Rather than just having metal with its metal ions, we can look at mixtures of metal ions. So say our two substances were, if we're looking at Fe3 plus and Fe2 plus, that half equation, that half cell, they're both solutions. So what we do there is we use a platinum electrode to dip into it. Right? So the platinum electrode is able to conduct the electrons away, but it's not very reactive. Right? So it's not going to take part in the reaction, but it's going to allow a circuit to flow. Also, we might end up working with a gas. Again, we bubble that gas over a platinum electrode, dipping into a solution of its ions, and I've got my potential for generating electricity. In electrolytic cells, we are using electricity to make a reaction occur that maybe doesn't normally happen, or wouldn't normally happen, a non-spontaneous reaction. So if I'm dealing with a molten solid, like this lead iodide, and I think, well, what's in that molten solid? So this is represented as a liquid there. Oops. That's what I've got, two of those. Then my lead 2 plus ions are going to head over to the negative electrode, where they are going to pick up electrons to form lead, and at the positive electrode, my iodide ions are going to be attracted over to that, where they are going to give up electrons to form iodine. And so here, where I am gaining electrons, this is a reduction. Here I am losing electrons. That's an oxidation, which means that this electrode is the anode, this electrode is the cathode. So this is maybe what you're familiar with from physics. it's kind of the other way around with the other circuit. So the important thing for us chemists is that we look at oxidation is the anode, reduction is the cathode. But you can see there I'm reducing my lead ions to form lead, I'm oxidizing my iodide ions to form iodine, and I'm getting conduction in here through these charged ions which are able to move around. So we can work out what we're going to get from each of these molten solids. So if I look at what ions are present, I've got magnesium and I've got bromide ions. What's going to happen at the anode where I've got my oxidation going? Well, my bromide ions are going to form bromine, and over here my magnesium ions are going to be picking up electrons to form magnesium. And you can work through these. You're going to see iodine forming here, you're going to see copper forming there, you're going to see oxygen forming there, you're going to see aluminium forming there. The nitrate, something complicated like that, you're going to end up seeing oxygen forming, and here you're going to get and so going back to that, you'll also probably find some NO2 being produced as well, but we won't dwell too long on that. Looking back up here, if we're looking at amounts of products formed whenever we're pumping a mole of electrons around the circuit, whenever that happens for the sodium and sodium chloride, I'm going to be getting a mole of sodium produced. However, notice that I'm going to be needing 2 moles of electrons to move around the circuit to be seeing a mole of chlorine produced. So if I was counting my number of moles in that situation, I would find I end up with twice as many moles of sodium as I would of chlorine. Now that's just a little side point. So that is what we've been through very quickly.